talks in optical tweezers. Firstly, let us try and understand what an optical tweezer is. By the way, this is briefly my outline of the talk. I will be covering this talk in two parts. In the first part, we are going to understand the fundamentals of optical trapping. We will begin with what is an optical tweezer, go on to some details concerning it, and then we will do a little bit of a hands-on session using MATLAB, wherein we will use something called as the Optical Tweezer Toolbox, which is developed by Professor Helena Rubinstein Dunlop's group at the University of Queensland in Australia. Okay, so let's get on with the talk then. So Kepler.
Sorry to interrupt. You please run it in the presentation mode so that the full slide will be visible.
Yeah. Is this visible now? Okay.
Yes, it is.
Yeah. Okay. Yes. So Kepler made the following. Was that when comets approach the sun, number one, their tails get elongated, and number two, the direction of the tail gets pushed away from the sun. So what does this imply? This implies that light can push particles, which I've written here. Correct. So then we ask the following question. We know that, yes. So we know that light can push particles. We have just seen that. Therefore, can light also pull particles, or can light trap particles? So if we ask this question, we end up with the optical tweezer. The optical tweezer itself was discovered by one Arthur Ashkin in Bell Labs in the United States of America. What he saw was that if he had an intense beam of laser and he passed it through a suspension of colloidal particles means tiny microscopic objects, right? Milk is a colloidal particle. Blood is a colloidal mixture. So in blood, we know that there are red blood cells which are suspended in a buffer. Similarly, in milk, we have little globules of protein which are suspended in yet another buffer. So similarly, if you take polystyrene beads and suspend them in water and you pass an intense beam of light through them, instead of getting repelled, like what happened in the case of a comet approaching the sun, these particles approached or got pulled towards the laser light. So Ashkin made this observation in mid-70s. Okay. And then from the mid-70s, he worked and worked for another decade, and he perfected the optical tweezer. What he really did was he took something called as a high numerical aperture objective lens. Okay. He took a highly focusing lens. That is what it is. The high numerical aperture objective here. 1 second. Let me pull my laser pointer. Yes. So this is a high numerical aperture objective. And if you pass an intense beam of light, namely the laser light, through it, then at the focus, you have enough of a force to capture tiny particles through which, oh, sorry, I seem to have done something. I lost the PPT. Yeah, I got it back. Madam, is my PPT still seen?
Yes, sir.
Okay. So now he saw that instead of simply being gently attracted like his 1975 experiment, this time around, if you focus the light down to something called as the diffraction limited spot, then you can indeed trap particles in 3 dimensions at the focal spot. Okay, so this really was the discovery of the optical tweezer, and he took 10 years to perfect this. perhaps this is a lesson to all the young researchers here, to sort of stick to one problem and keep on working on it, right? So because in the mid 70s, he saw that these particles are gently attracted to the laser beam. So from there till development of the optical trap in 3D, it took him 10 years. Okay, so now let's try and understand what exactly is happening in an optical tweezer. In an optical tweezer, if the bead is ever so slightly displaced, then due to the refraction of light through the bead, you will have almost a harmonic trap, which will try to pull the bead towards the center of the laser spot. That is what is shown here in this diagram. This is analogous to a mass suspended on a spring. So if you stretch the spring slightly, so then the spring will pull back on the mass and it will try to bring it back to its original position or the mean position. Okay, in such a situation, what we generally see is that there are two forces acting on the bead. By the way, mind you, this bead is a few micrometers in size. So this is maybe 3 micrometer in size. To give you some rough idea, human hair is about 50 micrometers. So this bead is about, if you take it as 5 micrometers, 10 times thinner than the thickness of the human hair. So it is really a very tiny bead, and the focal spot here is about 1 micrometer in size. I'm sorry that I have shown here the spot to be larger than the bead. In fact, it's the other way around. The bead is slightly larger, around this much, compared to the focal spot here, which we also call as the beam waist. Okay. Any doubts still here? Or should I just continue? Okay, so I will go on then. So now, in such a situation, when a bead is trapped optically, there are two forces acting on it. One is called the scattering force, the other one is called the gradient force. What you saw in case of the comet being pushed by the sun's light is essentially scattering force. So this force will try to push the bead away along the direction of propagation, like that. So here, this arrow shows us that the laser light is traveling from the bottom of the screen to the top of the screen, right? Like that. So the scattering force will be along that direction, bottom of the screen to top of the screen. Okay. So now, because of the strong focusing of the laser, you have something called as the gradient force. So the gradient force is going to act like the spring. It is going to bring the bead back to the center of the spot. Okay, so that is really the job of the gradient force. And this is seen only when you strongly focus your laser beam. Okay, which means you will have to pass it through what we discussed earlier, the high numerical aperture objective, which is shown here. Right? So that's really how the optical tweezers work. Before I get into the two scattering regimes, let me just discuss this with you. Now, along the x-axis, I have distance. So that's my laser beam direction. And the origin here is the focal spot, is the focus of the laser. Now, what we saw here, the two forces, the scattering force and the gradient force, are plotted out nicely for you here. So in green, in red, you see the gradient force. It is passing through 0, right? Now in blue, you see the scattering force. You must also note that the gradient force goes towards the negative direction. That means the gradient force is directed towards the focal spot always. Whereas the scattering force is always positive, which means it tries to push the bead away from the focus, whereas gradient force for positive Z is negative and it will try to bring the bead back to the focus. So similarly here, because Z is negative on the left side, the gradient force is positive. Okay, so this will try to push it up if the bead goes down. Similarly, if the bead is above the focus, then the gradient force pushes it back. Okay, whatever it is, gradient force is always trying to bring the bead to the focal spot, whereas scattering force is always trying to push the bead away from the focal plane. Okay, now depending upon the size of the trapped object, we can have two regimes of force calculation. These are approximations, both ray optics and Rayleigh scattering. If the object is very large compared to the wavelength, that is, if it is 10 times the wavelength used, then you use something called as the ray optics regime. Now, similarly, if the object is about 1/10 of the wavelength that you're using, then you use something called as the Rayleigh approximation to write down the forces. Now, what is the most general scattering technique used? The most general scattering technique is the Mie scattering, wherein you write the full Mie theory to calculate the forces on the trap bead. I'm sure experts in the audience will immediately see some relevance to various other scattering phenomena encountered in physics, be it in nuclear physics or even in condensed matter. Okay, so now I'll go back a bit and tell you a little bit about ray optics. So how does ray optics works? Like we saw earlier, this is a Gaussian profile of the beam, and this is my bead, which is displaced now towards the left. So as you can see, there is a thicker arrow that I've drawn for rays coming from the center. Because of the Gaussian profile, they carry a higher intensity. Whereas rays from the edge of the beam are shown in a thinner ray, which means the force they impart is, lesser in magnitude compared to what we have here on the right side. So you can use simple physics to infer from Newton's third law that the reaction force or the net force will be towards the right. Okay, so if the bead pushes to the left, then the light pushes to the right. Similarly here, if the bead is above the focus, then the light, if the bead is below the focus, then the light pushes it above. Okay, so this is really the ray optics regime. And in the Rayleigh regime, we approximate the bead by the induced dipoles in it, and by simply noting down the polarizability of the material, we can very simply compute the force on it using this particular expression. So why is it important to know forces on trapped entities? It is important to know forces on trapped entities because these beads are also used as a force readout. So, for example, these beads are sometimes stuck to biological species. And if you want to really measure, for example, let's say the fluctuation of a membrane, what you do is you stick these beads to the membrane that you want to measure, you want to study. And then by looking at the force it takes, right, the force balance between the membrane, let's say, pulling the bead to the left and the light pulling the bead to the right, you can infer by knowing the displacement of the bead from the center of the beam how much force is it with which the membrane is pulling the bead, which means you have measured the fluctuation force of the membrane. So you have many such examples in colloidal physics and also in biological physics, right? So you could, in colloidal physics, you could imagine two beads in two independent traps held very close to each other. And then if there is some kind of interactive force between the two beads, then by simply knowing the fluctuation of the bead, you can measure the interactive force between the two beads. Okay, so therefore, trapped beads act as force readouts, microscopic force readouts, mind you, and therefore it is important to know the forces on these beads. Right. Uh, with this, I really would be ending the little introduction that I wanted to give you about optical tweezers, and then I'll try to demonstrate a little, simulation which is readily available on the internet. Now, I told you me regime is the most general regime. It doesn't approximate the bead to be smaller than the wavelength, greater than the wavelength, nothing. Uh, what it simply does is that it takes the incoming beam as a series of spherical harmonics. What are spherical harmonics? I would perhaps take you all back to first year MSc, wherein we learned that there is the dipole term. There's a monopole term which looks spherical. Then there is the dipole term which looks like two lobes. Then there is the quadrupole, then there is the sextupole, octupole, etc. Right? So these are really the spherical harmonics. So because the incoming beam is highly curved, you will require spherical harmonics to write down its shapes. And that is what you essentially do in spherical harmonics. You write the incoming beam as a certain percentage of monopole, a certain lesser percentage of dipole, a still lesser percentage of quadrupole, so on and so forth, till you have a good convergence. And then you write down, as usual, the T matrix for the bead, and the scattered beam is simply computed as T matrix times the incident beam. Once you know the scattered beam, you've written down the input beam, correct, in step one. You computed the scattered beam here. So then what you do is you simply write the force as the difference in the two momenta, that of the incident and the scattered beams. Okay, that multiplied with the size of the beam, the bead, is going to give you the torque. Okay, so that's essentially how you go about determining force and torque. Before we could go on to the demonstration, what I'll do right now is I will try to bring up the simulation that is uh, in the it's by I think the University of Colorado at Boulder. Just give me 1 minute where I will stop sharing my screen so that I can bring up that simulation. Yeah, I'm trying to bring this up. In the meantime, what I'll do is perhaps I'll try and copy the link and put this on the chat here. Madam, can I paste this link in the chat?
Yes, sure. The chat box is there at the bottom.
Okay. Okay, madam, I've just sent this. Madam, this seems to be not taking it. Just one sec. I'll just put this in WhatsApp. Maybe you can paste it.
Okay, so no problem.
I put this in the RP group.
Yes, sir, fine. I will get it here in the chat
Yeah.
box.
Yes, ma'am. Just so that participants can play around and uh, try to discover for themselves whatever they want to know.
Yes, I have pasted it for everyone in the chat box. You can just
Yeah.
click and go ahead.
Yeah. Yeah. Okay. So is my screen visible again or?
No, you have to
Okay.
start sharing again.
Oh, okay. Okay. Yes, ma'am. Desktop share. Okay. Yeah. Yeah. Is this seen now?
Yes, sir.
Okay. Yeah. So this is, from the University of Colorado at Boulder. You see that there is a strongly focused laser beam, and then there is a bead. The reason why it's jiggling around is because it's in water. Okay. So let me bring up the ruler also. Yeah. So there you can see that this is really in terms of a few nanometer, the displacement of the bead. And the bead itself is about 100 nanometer um, in radius. Okay. So now let's also enable the optical trap force on it. I don't know if you can see at the center. There are two arrows there. So one is the drag due to the water, and then the red arrow is really your optical force. So you see that the bead is not jiggling away and moving away from the focus. The beam is really pulling it back. Okay. So beam is really pulling it back. Uh, Let me increase the laser power here. So right now this is at 500 milliwatts. So if I increase this, if I double the power, you can see that the jiggling is reduced somewhat. Now let's do the opposite. Let's decrease the power. So this is 0, which means the laser is off. So now the bead is, as you can see, it's making longer excursions from its mean position. Okay. Now let's turn on the laser back. Yeah, there you go. It's trapped once again. Yeah. So this really, it tells us something about the trapping. And here we can bring up a position, and this will tell us, yeah, so this will tell us how really the bead is behaving within the trap, and based on the positions here, you can compute the trap stiffness. Okay. So now there are other sections here. fun with DNA. So this thread here is really the DNA. If you want to measure the elasticity of DNA, you can again do it from the optical tweezer, right? So this is again all in water. So this is Brownian motion, which is causing the bead to jiggle. Along with the bead, the DNA strand which is stuck to the bead is also jiggling around. And by measuring the displacements of the bead, you can infer the force on it, and by simple math, you can therefore infer um, the elasticity as well. Okay, so the use of optical tweezers really, while it is definitely something that colloidal physics has been using, the real use of optical tweezers has been in biology, particularly in biophysics, right? So yeah, I think maybe I'll stop this. And I will come back to my screen, stopping the sharing. And yeah, as per my plan, we thought that we will have some 5 or 10 minutes of questions and then move on to the demonstration. Yeah, the panel is open for questions.
Yes, participants, if you have any question, you can directly ask or you can put it in the chat box. I will read it for you. No questions yet.
Okay. Okay, ma'am. I'm just trying to load my MATLAB. Giving me some issues. Just a second, madam. Yeah. So MATLAB is loading now. Just give me one more minute while it loads. In the meantime, if there are questions, I'm happy to answer.
Excellent, sir.
Yes, sir.
Sir, can we use this optical tweezers in nano devices, any nano applications in
Yes,
devices?
sir. Yes, sir. Most certainly, sir. It is
Where,
being
sir?
used in a gamut of nano applications. Like I
Uh,
said, to measure, the interactive forces between two colloidal objects, two nanoscopic objects, it is being used, and also
uh, uh,
it is being used in something called lab on a chip.
uh, uh,
You have a tiny assay, microscopic assay, wherein
yes,
you
sir.
have all these microscopic pipes through which there are, flows,
Yes,
fluid
sir.
flows. So there you can gears and levers. So that's where
Fluid mechanics related things, sir.
yes, sir. You can think of it like that. It is fluid mechanics, it is colloidal physics, biophysics. One or two things I think we discussed. So it's got a wide variety of applications these days.
Okay, sir. So can we do any research in computational thing also on tweezers?
Yes, sir. So computing forces is a big challenge. So we talked about computing forces in simple beats. Now, what about complex cells? Correct.
Yes, sir. Yes,
Red
sir.
blood cell, or even you could have any kind of epithelial cells, healthy epithelial cells, cells that are affected by disease such as cancer. In such situations, measuring membrane stiffness, etc., becomes extremely important. In fact, one of my first works to come out from my PhD measured the membrane stiffness of red blood cells, healthy red blood
Nice.
cell and red blood cell of diabetic person.
Okay,
So
sir.
we found that the membrane stiffness of the diabetic red blood cell is much higher than the membrane stiffness of healthy person.
Okay,
So
yes, sir.
this is very important because in case of diabetes, we say that wounds don't heal easily.
Yes,
That's
sir.
because in order to reach to the wound, the red blood cell will have to pass through extremely narrow capillaries. So it will have to squeeze through those capillaries. So if the red blood cell has become stiff, then it will not
Yes.
be able for it to pass through narrow capillaries by squeezing through them. So that is the reason why wounds don't heal easily in case of high diabetes.
Okay, sir.
We found the number, the actual membrane stiffness. We have measured it using the red blood sensor.
Okay, sir. Thank you.
Yeah. So can I now get back to my presentation, ma'am? Hello.
Yes, sir, please.
Yeah. So my thing is loaded. ये कहाँ हो गया? हाँ. So ये हुआ Zoom. हाँ. Yes. So I have to share once again, no?
Yes, sir.
Yes, ma'am. So I'm sharing here. So this is my MATLAB screen. So this here you will have to install something called Optical Tweezer Toolbox. You can just search for Optical Tweezer Toolbox on Google. Okay, so it is developed by Dr. Helena Rubinstein Dunlop's group in University of Queensland. So that you will have to download, and in MATLAB you will have to set your directory to that particular folder where you downloaded the Optical Tweezer Toolbox. So it will be in a zipped format. You will have to unzip that, and that folder you will have to choose as current folder here. I don't know if participants are using MATLAB. So if you're not using MATLAB, if you are on Linux, Octave will also work well. So this package works with Octave also. Okay, so I'll perhaps then move forward then. So you can of course do MATLAB programming, but I thought maybe we will do some sort of visualization so that things become simpler. So the command to type in order to bring this graphic user interface up is ott.ui.launcher. I don't know if you can see my command window here. Can you see
Yes,
my
sir.
command
Yes.
window? Yes,
Yes,
so
sir.
that is yes, sir. So that is the launcher. Okay. So then go to BSC. So BSC is short for beam shape coefficient. Beam shape coefficient kya hua? So we said that in me scattering, we are going to write down the incident beam as sum of monopole, dipole, octopole, sextupole, etc., right? In front of each of these, there is a weight parameter or coefficient. That is called beam shape coefficient. Okay, so we are going to now set up our beam. Okay, so I'm going to say BSC, beam shape coefficient, and then it says LG beam. Okay, so I'll simply say launch. I think it's not taking one sec. Yes. Okay, so you get this window, generate LG beam. LG is Lagarde Gaussian beam. So Lagarde Gaussian beam is the most general beam. Correct. So this is first year electrodynamics, Griffiths. Correct. We have various beams, and they all can be written down as different kinds of LG beams. What we are using is a Gaussian beam. Gaussian beam is what? LG00. Radial mode is 0, azimuthal mode is 0. So that is the reason why here, if you can see, I've set radial mode to be 0, azimuthal mode to be 0. So then polarization, if you set this as 1, that is going to give you circular polarization. If you set this to 1, then it will be polarized along x-axis. If you set this to 0, 1, okay, so then that will be linear polarization along y-axis. So if you want elliptical polarization, you play around with the coefficients, maybe 0.5, 0.5, or you can compute that, I'm sure. Power, we've set it to 1 unit. Okay. Now, wavelength in vacuum is specified to be generally 1064 micrometers is used. 1064 micrometer is a very special wavelength. It is near infrared wavelength. The reason why we use this wavelength in experiments is because biological species don't absorb this wavelength. Okay, so they're mostly transparent in that window, in the near to mid infrared window. And that is the reason why 1064 is used. And 1064 is a very popular wavelength. I'm sure the experimentalists in the audience will know this. So this is the Nd:YAG laser. Correct? So we will set this to be 1064 micrometer. Now, index medium. So we will set this to be water, 1.33. And then comes Na. Na is what? Na tells you how strongly your beam is focused, right? So let's set this to 1.2. And Nmax is what? Nmax is telling you how many terms to use in your expansion. So there is monopole, dipole, sextupole, octupole, etc., right? Quadrupole. So how many such polars or how many such poles to use? So that is Nmax. We'll set that to be auto. There is actually a relation for this, but for our purposes, it's enough to set it to auto. And then we say generate. Yeah. So this is giving us the beam. You can visualize this here. In the XY plane, it looks like that. Correct? So this is the airy beam. When you strongly focus a beam, you get the airy disk pattern, right? This is again, if you have done optics in your MSc physics, this is perhaps something that you would have encountered in your third sem, right? Third sem or second year. And now how does it look along, let's say, XZ? So this is how it looks. Okay, so our beam is generated. What have we called it? We've called it as beam. So let's close this. Now let's go to the T matrix. What does T matrix give us? T matrix gives us, so T matrix gives us the transfer matrix for the particular beam, the bead that you're using. So let's go with this. Sorry, I think this is asking for load. Okay, geometric shape. Let's go with this. Yes. Okay, so we've chosen sphere. This is how it looks. We've set its radius to be 1 micrometer. Okay, and this matrix that is being generated, we've chosen to call it T matrix. Now you have to set the relative index. Relative index is what? Index of this material divided by refractive index, correct? So if you take 1.59, let me quickly do that here. 1.59 divided by, we took water previously, 1.59 divided by 1.33. So this is 1.19. Yeah, so it's already set to that, 1.2. Okay, and wavelength in the medium, it says. So here you will have to take 1064 and divide it by 1.33. So you're going to get how much? 800 nanometers. But here everything is in microns. So this is going to be 0.8 microns. Okay. So method is already set here. It's not highlighted. It's set to me. So now I'm going to say generate, and now the T matrix is being generated. So here in the workspace, the MATLAB workspace, you can see that the T matrix is being generated. Okay, so now let me close this. Now I go to tools, and I will launch the force profile. Okay, so let's choose whatever we set up previously. And now what we are doing is we are translating the bead along Z direction. So if we move this along Z direction, how does the force look? So that is what we are calculating. So I will say calculate. And this is my force profile. Okay, so it's giving me, I don't know if it is visible here. So the Z force is actually going to negative as the bead is going to is moved along positive Z direction. So similarly, if the bead is moved along the negative Z direction, this is positive, which means it is trying to always pull the bead towards the center, okay, or towards the focal spot. And this is the torque. Now here, you must note that on a sphere, there is really no torque because of symmetry. Now, on the other hand, if you took asymmetric shape, like an ellipsoid or a disc or any such shape, cylinder, then torque becomes extremely important. I think due to lack of time, we may not be able to cover that, because I'll also have to tell you the theory behind it first, and that itself will take me time. So here, since it's simply an introduction, we are going to look at the force on a spherical particle. Okay, and this is essentially the range that you can choose. You can choose it to be translated from -2 microns to +2 microns. Okay, so this is really the force torque profile. If you want, if you are well versed with MATLAB, you can go here, bring up the force torque, and copy this down to Excel or whatever you prefer, and you can do all kinds of um, you can try out various things with it. Okay, so this is really what I wanted to show you, and maybe now we will stop and discuss this at length. I don't know if the participants are doing these computations parallelly, but I mean, if there is someone who's trying this out and you're having some issues, I can always help you out. Yeah. Assignments, I would say that you try out different sizes of the bead, correct? So where do you set the bead size? You set the bead size in T matrix. My first assignment would be for you to change the bead size and look at what happens to the maximum trapping force. Start from, I think we did 1 micron, start even lower, start at, let's say, 100 nanometers and go all the way up to 10 microns. And for each of the bead size, uh, please give me what is the corresponding maximum force. Maximum force means the negative here, the negative of the force curve here. Okay, you can just use the readout and simply note what is the y value. That is more than sufficient. You do this for all the bead sizes. Start from 100 nanometer. Initially you go in steps of 500. So 100 nanometer, 500 nanometer, 1000 nanometers. So that is 1 micron. And then you go in steps of 1 micron, go all the way up to 10 microns. And please tell me what is the maximum y value you get here. So that will tell you how the optical force varies with the bead size. That is one thing. The other thing, the second problem that I want the participants to try out is to play around with the numerical aperture, which was here in the BSc module. Correct? So in the BSc module, there was something called the numerical aperture, NA, right? So zero point 0.9 is what it defaults at. Go to even a lower numerical aperture, let's say 0.6, and see if the trapping really happens. Okay. You will see that the force curve you got, it will begin to flatten out as you decrease the NA. Anyways, I won't tell you what happens. So start with 0.6, go in steps of 0.1, 0.7, 0.8, 0.9, 1.0, 1.1, 1.2, if you want 1.3. And tell me, for the same bead size, how does the trapping force varies with NA? Okay, so these are really the two questions I want people to try out. Number one, variation of trapping force with bead size. Number two, variation of trapping force with numerical aperture. Okay, I think if you do this, you'll get a very good sense of how optical tweezers work and how force calculations, etc., works. Okay. So you can also Google optical tweezer toolbox manual. Okay, so there's an entire website. They've made a nice website for this. You can bring up that manual. You can look into the manual there, and you can play around with this. Right. So I think I thought I would do a slightly complicated problem, but I soon realized that doing anything more than this would require, at least 1.5 hour of rigorous theory. And only then can we do the calculation. Only then it will make sense. Okay. Yeah, I think I'll stop here. If you have any questions, please ask me. I'm more than happy to answer.
Sir, how to launch the MATLAB?
Good evening, sir. Good evening, sir.
Yes, sir. Tell me.
Sir, I am beginner for MATLAB. How I can learn MATLAB application?
Yeah, so you don't need a lot of MATLAB expertise.
Okay, sir.
Maybe if you spend half a day trying to understand how MATLAB handles matrices, right? If you
Okay,
learn
sir.
just that much, then it should be more than sufficient for you to use the optical tweezer toolbox. You
Okay,
can
okay.
start using start doing this with the user interface, and then later on you can make more complex calculations.
Okay, sir. Thank you, sir.
Yeah, thank you, sir.
Any other questions? If the participants are having, you may directly ask or you may put it in the chat box.
Yeah, I would encourage everyone to strongly look at the Optical Tweezer Toolbox manual. It's also freely available. Just Google Optical Tweezer Toolbox manual, you will get it. Look into it. There is much more explanation, and you can try out various things that they're suggesting there.
There is
Oh,
one question from Dr. Rashmi Deshpande.
yes, ma'am.
Why the bit size should be bigger than the beam width?
That's a very good question. If you're using Gaussian beams, what happens is that because of the Gaussian profile, the scattering force is maximum at the center. Now, the gradient force comes from the edges of the beam. Now, if you have a small bead, it will not go to the edges of the beam at all. Therefore, it will not experience gradient force, which is really responsible for trapping. It will only experience the scattering force, which tries to push the bead away. So that is the reason why 500 nanometers is what is typically the lower limit for optical trapping using a 1.2 or 1.3 numerical aperture objective, which gives you 1 micron spot size. So the sweet spot really is bead size equal to spot size. So that is where you will get maximum trapping force for the power that you are putting in.
Excuse me, sir. There are
Yes, sir.
many websites for optical tweezers toolbox manual. Which website we have to use for this practice, sir?
Okay, sir. I'll just give it to you. 1 second, sir.
Yes.
Yeah. How do I? Madam, it says chat disabled.
Is it, sir?
Yeah, madam, I'll send you on the resource person group.
Okay, fine. No.
Yeah, send you, ma'am. So you can just put it in the chat.
Yes, I have put it in the chat box for everyone.
Yeah, I mean, now I think my job is more or less done. It is up to the participants really to uh, try out these simulations or calculations and come up with interesting questions.
Yes, and we will definitely urge the participants to go through the instructions, go through the resources provided to you. And even if you are having any doubt, the resource persons are there in the group, so you can always ask.
Yes, ma'am. Out of the two problems that I gave you, let's see if we can do at least one of them right now, because we still have another, I think, madam, 45 minutes. I think we can do one problem at least.
Yes, sir. Go for one more. Yeah. We can. Hello. Hello. There is a question from Aparna.
Yeah,
Yes,
yeah,
ma'am.
Please ask.
So, yeah, so can we do it in a Scilab? Like MATLAB is not
Yeah.
open source.
Yes, Scilab is also compatible. Yeah, you can do it.
Oh, okay.
Just
Thank
just
you, sir.
make sure that there, when you set the directory path, set it to that folder where you unzip this toolbox.
Okay.
Yeah.
Yes, sir. I will try it in there.
Yeah.
Thank you, sir.
If there are no more questions, we can proceed ahead with the session. I will put the links in the WhatsApp group as well. Both the links which the resource person has provided today.
And go ahead. I
I
think there
suppose
are
there
no
are
more
no more
questions.
questions. Yes.
Yeah,
I
move
would
ahead.
like to request the chairperson of the today's session, Dr. Akhilesh Ugle sir, if he has some queries to ask, or rather, if he doesn't, he can summarize the session for us. Please, sir.
Uh, Praveen sir, hello, am I audible?
Yes, sir, you are.
Yes, sir.
Yeah, yeah. Praveen sir, do these optical tweezers have any applications in quantum computing or quantum computing technology?
Uh, Not at the moment, sir. But
Okay,
they are using this in something called quantum metrology. Okay.
okay,
So there is one group, namely Kishan Dolakia's group,
okay,
based out of Scotland, at the University of St. Andrews, wherein what they do is they trap these particles, these microscopic particles, well, not even microscopic, nanoscopic particles in vacuum. That is one thing that I did not discuss today.
okay,
But you can trap in vacuum also. It's ridiculously difficult because, as you can well imagine, you have to bring down the vacuum down to something like 10 power minus 6, 10 power minus 7 torr. You have to maintain the vacuum, and then you have to inject these particles, and then you have to trap them. So trapping in air or vacuum is much more challenging than trapping in water. But once you trap these particles in air, if these particles happen to be birefringent, then using circularly polarized light, you can rotate them at extremely high speeds. In fact, the record today stands at something like 10 power 8 rotations per minute. So at these high rotations, you do have some quantum effects uh, showing up, and that's why this is called quantum metrology.
okay, sir.
Yeah. So you can look up Kishan Dolakia,
Yes, sir. Yes, sure, sir.
trapping, optical trapping in air.
Yeah, okay. Thank you, sir. Any other questions from participants?
It seems there are
Ma'am,
no
should I,
questions. Yes,
right,
yes.
should
Please
I
summarize the
proceed for
session, sir.
conclusion? Yeah, okay. Thank you, sir. Thank you, Praveen, sir. It was very wonderful session, very nice session. You have explained the forces and torques in optical tweezers particularly, and functional forces with a very good example of like forces on membrane. You also explain very good how this plays a vital role in like diabetic patient and normal patient, that the membrane becomes like rigid, or rather we can say stiffness will be there in the membranes, and how it will help in, or will not help in uh, wounds, healing the wounds. Okay. With the wonderful hands-on experience on MATLAB, I think more many participants might have learned how to use the tools on MATLAB. In fact, if they are beginners, as sir said, they could download the manual and they can proceed for their work in MATLAB also. So thank you, sir, for the wonderful session, and thanks a lot. And it was a completely interactive session. Thank you.
Thank you so much, Akhilesh sir. Thank you so much, Praveen sir. To offer the official vote of thanks, I would like to now call upon the patron and mentor of this workshop, a guiding force whose vision quietly shapes many meaningful academic initiatives. She possesses the rare ability to bring together eminent resource persons from across the nation, scholars who truly deserve commitment to strengthening computational approaches in physics, education, and research. Her mission has always been clear and inspiring to open the deeper, often unexplored layer of scientific knowledge and to make them accessible to next generation of scientists and teachers. Through her dedication, collaboration, and academic leadership, she continues to nurture a culture where learning goes beyond the surface and inspires curiosity, inquiry, and innovation. It is therefore a moment of honor for all of us to invite none other than Dr. Abha Khandelwal, patron and mentor of this workshop, to kindly present the vote of thanks for the session 3. Over to you, ma'am.
Namaste. Good evening to all. Thank you, Bhakti. As we
evening, ma'am.
reach the conclusion of session 3 of this national workshop, it is truly my pleasant duty to privilege to propose the vote of thanks. First and foremost, I extend my sincere gratitude to Mahesh Shetty sir, President, IAPT RC08, for being our collaborator. I also express our heartfelt thanks to Dr. Mansingh Takale, President, IAPT SRC, Sub-Regional Council, Kolhapur, for delivering the welcome address, which beautifully set the tone and spirit for the workshop. Thank you very much, Dr. Mansingh sir, though he has left because of his commitment, but still he joined us to bless us. Our deepest appreciation goes to today's eminent resource person, Dr. Praveen Parthasarthi, Assistant Professor of Physics, Dr. H. National College of Engineering, Bangalore, for his enlightening and insightful session on computational methods in optical trapping photonics, that is. His presentation clearly demonstrated how computational techniques enable us to model, visualize, and understand complex physical phenomena with greater clarity and precision. Thank you, Dr. Praveen. I would also like to sincerely thank the chairperson of today's session, Dr. Akhilesh Ogale, sir, Registrar, G.H. Raisoni Institute of Engineering and Technology, Nagpur, for graciously chairing the session and enriching the discussion with his esteemed academic presence. Thanks a lot, sir. A very special word of appreciation goes to our convener, Dr. Bhakti Patankar Rajavedya, International Relations Officer and Assistant Professor in Physics at G.H. Raisoni College of Engineering, Nagpur. We all know the convener is the backbone of the workshop. Dr. Bhakti, your careful coordination, hard work, and commitment has shaped this national academic event beautifully. Thanks a lot. Over the past few days, the workshop has explored important contemporary themes in computational physics, including physics-informed neural networks, computational luminescence, and computational methods in optical trapping, giving participants a valuable glimpse into how advanced computational tools are transforming research and teaching in physical sciences. The true success of any workshop lies not in the sessions delivered, but in the minds that absorb and carry the knowledge forward. Hence, I sincerely appreciate all the participants for graciously attending these sessions and meaningful engaging with these ideas. Your attentive presence, thoughtful interactions, and eagerness to learn have truly made the workshop lively, interactive, and intellectually enriching. Thank you, participants, and I would like to give my special thanks to Professor Lakshmikant Damodare sir. He is from my college, and I am happy that he joined the workshop. So thank you, everyone. Thank you very much. Over to host Dr. Bhakti.
Thank you so much, ma'am. Your words are always inspirational to us. And thank you so much, all the participants, for being attentive. That I have put it in the comment box that you please turn on your camera so that we can have the group photograph as well. So I can have the flowing of the screen. So still I can see some more faces turning on. So just hold on for a few glimpses. Yes, that's it. So thank you so much and have a wonderful evening ahead. Thank you so much, Dr. Akhilesh, Dr. Praveen, and Dr. Abha ma'am, and all my esteemed participants for joining today. Hope to see you on sharp 6:30 tomorrow. Bye.
Thank
Thank you,
you.
ma'am.
Thank you, Praveen sir. Thank you, Akhilesh sir.
Thank
Thanks,
you,
Thank you,
ma'am.
madam. Thank you for this wonderful opportunity.
Thank you, ma'am.